for this system of differential equations, we are looking at solving for x sub 1 and x sub 2, whereupon in this system we will let x be the dependent variable and t be the independent. And we have x sub 1 prime is equal to 2 times x sub 1 plus 3 times x sub 2. And we have x sub 2 prime is equal to 2 times x sub 1 plus x sub 2. And looking at setting things up and solving for this system of equations, and we have two major components, and we have with the coefficient matrix A. Okay, so we have from the system, so we have from the first equation, we have 2 and 3 with respect to what we have designated alongside x sub 1 and x sub 2. And we have in the bottom row, we have 2 and 1 referencing 2x sub 1 plus x sub 2, which we have defining the first order derivative of x sub 2. And we have with this two equation system, again we have our identity matrix I, which we have equal to where the top row is at 1, 0, and the bottom 0, 1. And setting things up in creating the pathway to the eigenvalues and the eigenvectors, we can take the difference between A and the product of the eigenvalue variable lambda times the identity matrix, and we have for A minus lambda times I, and we have substituting and subtracting the corresponding parts. So 2 minus lambda times 1 and 3 minus lambda times 0. So the top row we have at 2 minus lambda 3, and the bottom row we have 2 minus lambda times 0, which is 2, 1 minus lambda times 1, which we have at 1 minus lambda. And looking at the attainment of the eigenvalues, and if we take the determinant of A minus lambda I and setting equal to 0, and we have taking the difference between the diagonal products where we have 2 minus lambda quantity times the quantity 1 minus lambda minus 2 times 3 is equal to 0, and we have setting the equation up. Okay, so we have combining like terms, we have an equation that we have to be quadratic in the variable lambda, so we have lambda squared minus 3 lambda minus 4 is equal to 0, and upon performing the zero product property, okay, so we have with lambda minus 4 and lambda plus 1 as the factors, we have our respective eigenvalues, and it doesn't matter which order you place them, but I'm letting the first eigenvalue be equal to 4 and the second be equal to negative 1. And looking at what we have after the attainment of the eigenvalues, if we create the pathway to attaining the eigenvectors, and here we have in general terms, we have the quantity or the difference of A minus lambda I, where its matrix times the eigenvector V is equal to 0, and looking at what we have corresponding to each eigenvalue. So if I take the product, okay, where I have working with the first eigenvalue and establishing what the first eigenvector is going to be, and again with 4 as the first eigenvalue, we have A minus 4I, okay, times V sub 1 is equal to 0, where V sub 1 is in reference to the first eigenvector. And looking at what we have here, so for A minus 4I, and again, we have for substituting 4 for lambda, so you have 2 minus 4, 3, and 2, as well as 1 minus 4. So we have with our 2 by 2 result, we have negative 2, 3, 2, negative 3, and the first eigenvector we have generally designated as A sub 1, B sub 1 as the components inside this 2 by 1 matrix, and setting equal to 0. And we have 0 represented by the 2 by 1, 0, 0. And expressing what we have as an augmented matrix. Okay, so we take the top and bottom rows of A minus 4I as well as the rows of what we have from 0. So we have negative 2, 3, 0. and 2, negative 3, 0. And putting this in terms of the reduced row echelon form, would come out to 1, negative 3 halves, 0 in the top row, and zeros across in the bottom row. And for what we have in the top row, so we have a sub 1 minus 3 halves b sub 1 is equal to 0. And we have the relation that a sub 1 is equal to 3 halves of b sub 1. And with the zeros across, okay, there is no one placed in either of the coefficient matrix positions. So b sub 1 is regarded as a free variable. And with the fact that a sub 1 is equal to 3 halves of b sub 1, we have for the first eigenvector. So lining up what we have with a sub 1 and b sub 1, and a sub 1 is at 3 halves of b sub 1, and b sub 1 remains as it is, and taking the proportions, and so we have the ratio of a sub 1 to b sub 1 is going to be 3 halves to 1, and putting this in whole number terms, say if I multiply the top and the bottom values by 2, we have a 3 to 2 ratio. So the first eigenvector we can say consists of 3 and 2, but if you wrote it as 3 halves and 1 or any direct multiple, like negative 3, negative 2, or 6, 4, that would also work. Now, and looking for the second eigenvector, and again we had the second eigenvalue which was at negative 1. So for a minus lambda sub 2 I, we have a minus negative 1 times I, and this will translate to a plus I times v sub 2, v sub 2 representing the second eigenvector, and in the same follow through, treating negative 1 just as I did with 4 back in the matrix. So we have a plus I translates to 3 and 3 at the top, 2 and 2 at the bottom. And we got a sub 2 and b sub 2 for the second eigenvector. And again, we have 0 and 0 for the 0 matrix. And again, expressing what I have in the augmented matrix layout. So we got 3, 3, and 0, 2, 2, and 0. And the reduced row echelon form leads to 1, 1, and 0 at the top, and zeros across at the bottom. And we have from the relation, we got a sub 2 plus b sub 2 is equal to 0, from which we have a sub 2 is equal to the negative of b sub 2. And again, with the zeros across, b sub 2 is a free variable. And so for v sub 2, okay, again, we have in general terms, we had the setup as a sub 2 and b sub 2, and with a sub 2 equal to negative b sub 2, we're going to end up with additive inverses, and we can say that upon division by b sub 2 we have a negative 1 to 1 ratio, and you could also have written this as 1 at the top and negative 1 at the bottom, just as long as you have additive inverses contained in the matrix referring to the second eigenvector. And putting it all together, so we have for the solution set in x, we have is equal to the constant times the eigenvector times e to the eigenvalue times t. And since we have two distinct eigenvectors and eigenvalues, okay, so we have in expanding, we have x is equal to c sub 1 v sub 1 times e to the lambda 1 of t plus c sub 2 v sub 2 times e to the lambda sub 2 times t, and substituting. So for v sub 1, again, we had 3 and 2. First eigenvalue was at 4, and we have with the second eigenvector, we have negative 1 and 1, and again, the second eigenvalue was at negative 1. If you notice, we have this expansion, and if I take what I have in the top row, this will be in reference to x sub 1. So we have 3 times c sub 1 times e to the 4t, and you have plus negative 1 times c sub 2, or minus c sub 2 times e to the negative t. And for the bottom row, okay, this will be in reference to what we have for x sub 2. So we have 2 times c sub 1 times e to the 4t, and you have plus c sub 2 times e to the negative t. And you keep the numerical coefficients in front of the c's because we are trying to preserve proportions throughout. And so this will be your result in this case. For what we have in the next setup, okay, we have another 2 equation system, and looking at what we have here, okay, so the coefficient matrix, we have 6 and negative 7 at the top, 1 and negative 2 on the bottom. And we have, once again, for the two equation system, we have the same identity matrix. So we have, again, 1 and 0, 0 and 1. And take the difference between A and the product of the eigenvalue variable lambda and the identity matrix. So we come out to 6 minus lambda, negative 7 at the top. And on the bottom row, we have 1 and negative 2 minus lambda. And setting things up to find the determinant and setting equal to 0 to create the pathway to the attainment of the eigenvalues. So if I take the diagonal products, okay, so you have with the eigenvalue variable lambda, so we have taking the product of 6 minus lambda and negative 2 minus lambda, and deducting the product of 1 and negative 7. I went ahead and combined like terms, whereupon we have lambda squared minus 4 lambda minus 5 is equal to 0, and we have a factorable trinomial, and we have letting lambda minus 5 be the first factor and lambda plus 1 as the second. We had the eigenvalues at 5 and negative 1. And setting things up to find out what the eigenvectors will be. And with 5 as the first eigenvalue, we set things up to find out what the first eigenvector is going to be. So plugging in 5 back into the A minus lambda I matrix, and we had the top and the bottom rows will consist of 1 and negative 7. And again, we have V sub 1 is represented by the matrix consisting of A sub 1 and B sub 1. And again, we have 0 and 0 for the 0 matrix. And putting the setup here in augmented matrix terms and performing reduced row echelon form. So we have 1, negative 7, 0, and zeros running across. And from what we have from the first row, it turns out that A sub 1 is equal to 7 times B sub 1. And again, B sub 1 is a free variable. So we have with the first eigenvector, okay, we come out to 7 B sub 1 over B sub 1. So we have a 7-to-1 ratio. Okay, so for what we have here, expressing as an augmented matrix, so we have 3, 3, 0, 2, 2, 0. Putting in reduced row echelon form, we have 1, 1, 0 at the top. And again, the bottom row consists exclusively of zeros. And from the top row, we have the A sub 2 and B sub 2 are additive inverses. And B sub 2 is free. So we have for V sub 2, okay, we'll have negative 1 and 1. So looking at what we have in the solution set, okay, so we have x is equal to c sub 1 v sub 1 times e to the lambda 1t plus c sub 2 v sub 2 times e to the lambda sub 2 of t times t. And looking at what we have in the expansion, so we have with the top row sections, x sub 1 is equal to 7 c sub 1 e to the 5t minus c sub 2 times e to the negative t, whereas for x sub 2, looking at the bottom row sections, we have c sub 1 times e to the 5t plus c sub 2 times e to the negative t. And that is going to be the final result in this case.